last in the last lecture we have discussed a lot of examples of application of the dynamical equation that net torque is equal to moment of inertia into alpha for a body in pure rotation. And specifically, we have looked at the concept of the rotating pulley, which is an extremely important aspect of this chapter. So let's begin today with some examples further of the application of rotating pulley and spools. And from that point onwards, we will move on to the next aspect of rotational mechanics, which will be angular momentum and concept of angular impulse. So anyhow, let's begin. So we were going through the concept of rotating pulleys last time. So what we had basically understood is that when you have such a pulley which is having a free axle about which it can rotate freely without any resistive force or torque, and the surface of the pulley is highly rough such that the thread or string which is bound around it does not slip with respect to it. So in that case, whenever we have a situation where something like this is occurring, that if this is rotating with an angular acceleration alpha, it definitely means that the tension will be different on the two sides. Okay. And it also means that the downward acceleration of any point on the string here, or the upward linear acceleration of any point on the string here, that will be related to this by this constraint relation. The pulley has moment of inertia I and radius r. So this is the no slipping constraint relation. Okay. And net torque is equal to I alpha. So that over here will become T1 minus T2 into R is equal to moment of inertia into alpha. So this is the dynamics of rotation for the pulley. So these are the two equations that come into play. So the nature of the pulley, which is a rotating pulley, and the condition that the string is not slipping. So let us look at slightly more lengthy and complicated type of questions based on this rotating pulley concept. So now you'll see an example which has multiple rotating pulleys. So this kind of a situation, let's say we have two identical pulleys which are suspended like this. They can both rotate freely about their respective axes. And they are identical means that they have same value moment of inertia and radius. So this is now on this side we have attached a heavier block. On this side there is a lighter block. So given that moment of inertia of each of the pulleys is 50 kilogram centimeter square, and the radius of each one is 10 centimeters. Yeah. And mass of block A is equal to, say, 2 kilograms, and mass of block B is 1.5 kilograms. Take G as 10 meters per second square. You want to find the acceleration of the blocks A and B and the angular acceleration alpha of the pulley. So just start with this question. This will be a good revision of the application of concept of rotating pulley, which, as I told you, is very important. What we discussed in the last lecture. Please try this out. You additionally will need the free body diagram equations of the two blocks A and B. And apart from that, you can make use of the pulley equations that I've written on top. Okay. Just start making the free body diagrams and writing the equations yourself. I'll put up the equations in a minute. So at least make sure you got the equations correctly. If you're able to write down the equations properly with the parameters, then that's half the problem done. The rest is about solving the equations accurately, which will come with practice. Okay, so we will let's work out the question. So first of all, if the tension in this section of the string is, let's say, TA, okay, then the tension in this section will be different. Let's say it's T, and then the tension in this section will be further different.
Sir,
Because
but why tensions are different?
it's a rotating pulley, no? There is friction at the surface. So that creates a force in between, no? Where the string is in contact with the pulley.
Okay, sir.
Now, because their radii are the same, so this one will have the same alpha as this one, because you have the common value of alpha because radius is same for both the pulleys. So now from the free body diagrams of each of the things you can understand. So rotating pulley always, it has a rough surface, so the thread is not slipping on the surface. So it's gripping. So that creates the difference in tension at the two ends. And that's what creates the torque on the pulley. We saw in the above equation how the pulley is getting the angular acceleration alpha because of the torque created by the different tension on either side. If T1 is equal to T2, then net torque will be 0. So that will only be the situation where the pulley is not rotating. But here the pulley is rotating, so there has to be torque, so there has to be difference in tension. So now you make the free body diagrams of each of these items, okay, and be able to work out the equations. So far I've written only the
Where it is A is equal to R alpha, no?
that is a constraint relation, but the free body diagram equations you still have to write now. Constraint relation is just giving you one equation between A and alpha, but you have so many other variables to solve. There are
So
three
no, you have
different
written
tensions are
that
there.
alpha equal to AR, that's it.
Sorry, that's A is equal to R. Alpha should be A by R. So let's say this is pulley number 1 and this is pulley number 2. So now you have to consider all the forces and things. So on the block A, there is tension, there is its weight. It's going down with a linear acceleration. On this pulley, there is tension like this, and there is another tension like this. It's rotating like this. On this, there is a tension like this, another tension like this. It's rotating like this. On the block B, these are the forces. It's accelerating upwards. Okay. So the first equation is the constraint relation. So here, understand that radii are identical for both pulleys. So they have identical alpha. Okay, so there's only one angular acceleration variable. Now you write the FBD equation. So for the block A, for example, it is weight minus tension is equal to mass into acceleration. For the block B, it is tension minus weight is equal to mass into acceleration. Then you write the torque equations. So for the pulley 2, it is TA minus T into R is equal to I alpha. And for the first pulley, it is T minus TB into R is equal to I alpha. Because both of these are rotating clockwise. So you have to consider the clockwise torque. So now you see you have 5 equations and you have variables A, alpha, T, TA, and TB. 5
Sir,
variables
that
and
you
5
have
equations.
considered, no? That it is coming in right side down.
How do we know that? Because the mass of the block A is heavier, you can see. So this assumption is with this thing in mind that MA is greater than MB.
Okay.
So now substitute the values and solve these equations. Okay, 5 equations and 5 variables, as you can see, I've written on the side. So first make the FBDs and make sure you understand the equations, especially the torque equations with the proper sense, how we've taken clockwise torque. Okay, so hope the equations are all clear. Now let's come to the solving of the equations. So what we can do is you always start with the torque equations. So these two equations, divide equations by R and substitute alpha as A by R from the constraint relation in these two equations. So equation 4 will become like this, that TA minus T is equal to I by R square into A. Why I have R square in the denominator? See, because I've divided by R on both the sides. Okay. And then I've also substituted alpha as A by R. So there are two R's in the denominator. And equation 5, similarly, I've divided by R. So the left hand side will become T minus TB. Right hand side will become I by R into alpha, which is A by R. So I by R square into A. And you can check from the values I had given, I by R square will be basically equal to 10 kg, or what was it, 5 kg centimeter square. So 50 kg centimeter square, and radius was 10 centimeters. So let's substitute this. Okay. So 50 kg centimeter square divided by 10 centimeters whole square. So as you can see, it's 0.5 kg. So this equation will become TA minus P is equal to 0.5A, and this equation will become T minus TB is equal to again 0.5. Okay. Now bring in your second and third equation also. So your second equation, now the weight of this one was 2 kg. So 2g minus TA is equal to 2A, and this one was 1.5 kg. Okay. Because your MA was 2 kg, your MB was 1.5 kg. So these two equations have become like this one. Now you can see if you add all these equations, you will get rid of the term involving tension. Just add these four equations. So TA cancels out. See, this and this cancels out. TB cancels out. This cancels out. And T and T cancel out. Okay. So all those things are done. And we are left with just 2G minus 1.5G. And on the right hand side, we have 0.5 plus 0.5 plus 2 plus 1.5, that whole thing. So we have 0.5G. On the right hand side, we have what? 1 plus 1 plus 2, that's 3 plus 4.5 A. So A becomes G by 3. Sorry, G by 9. It's not 1.5, it's 0.5. So 4.5 divided by 0.5 will give us 9. So G by 9 becomes that. So this technique of solving the equations is very important. Okay. So I'll just make a note of it. So what we do here, okay, in the torque equations, okay, first divide the equation by R. Okay. And then substitute alpha equal to A by R. Okay. So then these equations can be solved with the other force equations which are there from the FPDs. Okay. So this is the technique of equation solving. Please understand this technique, how we applied it over here. It's very important.
Sir, you added that all four equations.
All the four equations are added. So all the three tension terms are getting cancelled, and we are just left with the 2G minus 1.5G. You can check. There's a TA, there's a minus TA, there's a TB, there's a minus TB, there's a minus T and a plus T. So all the tensions are getting cancelled. Understood now?
Yes.
Okay. Okay, so the linear acceleration is coming g by 9, okay, which you can now understand is
Yes.
10 by 9 or nearly 1.1 like that. Just per second square, okay. And the angular acceleration, which is e by r, will become 10 by 9 into the radius was 10 centimeters. So in radians per second, it will be 100 by 9. So 11.11 radians per second square. Okay, now next thing we will
Sir,
understand in rotational mechanics
sir,
is
1
the
minute.
concept of, yeah, sorry.
Sir, 1 minute. That last. Done, sir.
Okay. Next, we will understand the concept of angular momentum and impulse. Again, we will understand in the context of for a rigid body with a fixed axis. So basically, the case of pure rotation. So angular momentum, it is just defined in this way. The symbol for it is L, and it is moment of inertia into angular velocity. But here, L is defined as the angular momentum about the fixed axis. So angular momentum is also an axial vector, like angular velocity, angular acceleration, torque, etc. This is also an axial vector. So it's defined in the same way. The axis, according to the right-hand system, the direction of the axis is the direction of the vector, and omega is the angular velocity. Okay. Again, about the fixed axis. And of course, I is the moment of inertia, again about that same fixed axis. So when we define the equation this way, L is equal to I omega, all the quantities L, I and omega are about the same fixed axis, because the whole body is in pure rotation about the same fixed axis. Okay. So if this is, let's say, a rigid body, and it's got a fixed axis here about which it is rotating, then angular velocity omega, that is how it is defined. Okay. So this simply comes from the idea that for pure translation of a rigid body, okay, the linear momentum is defined as total mass into velocity of center of mass. This is how linear momentum is defined. So the rotational equivalent of this in pure rotation, the angular momentum. So replace linear momentum with angular momentum. So mass with moment of inertia and velocity with angular velocity. You can see the correlation between them. So it's like a rotational version of the linear equation. Okay. And likewise, for dynamics of pure translation, we have that net force is equal to rate of change of momentum, which becomes mass into acceleration for a rigid body. Okay, because its mass is fixed. So likewise, for dynamics of pure rotation, the net torque is actually defined as the rate of change of angular momentum, which further becomes I alpha. Okay. So additionally, we have the relation that the net torque about the axis of rotation is equal to rate of change of angular momentum with respect to the axis of rotation. Now L is equal to I omega. So rate of change of angular momentum becomes I into d omega by dt. So that's I alpha. Again, the idea here is because the moment of inertia of a rigid body, okay, about a fixed axis is constant. So when we express the rate of change of angular momentum, I is treated like a constant. So it becomes I into d omega by dt. So you can see that this equation here is analogous to this equation, that net force is equal to rate of change of linear momentum. Just as this equation here is analogous to this one, that angular momentum is equal to moment of inertia into omega, where linear momentum was mass into linear velocity or mass into simply velocity. Okay. So this is how we describe angular momentum of a rigid body about a fixed axis, and that is the relationship of angular momentum with respect to the net torque. That net torque is equal to rate of change of angular momentum. That's the dynamics of pure rotation. Just like the dynamics of pure translation was that net force was equal to rate of change of linear momentum. So just make a note of this, then we will look at applications of this. We'll also discuss the concept of angular impulse. This was the concept of angular momentum. Now we'll discuss the concept of angular impulse, and then we'll see how to connect them in application examples. Okay, so hope this
Sir,
part is
1
clear.
minute.
Okay.
Runs.
Okay, so now that we understood the concept of angular momentum, next thing is the concept of angular impulse. So angular impulse due to a torque acting for time delta t is tau into delta t. That is the angular impulse. If the torque is constant or tau dt integrated from 0 to whatever time, if the torque is variable. So again, this concept you can understand that is coming from a direct conversion of translation to rotation. When we talk about pure translation, in that we talk about linear impulse, linear or translational impulse due to force F. So it was defined as F delta T or integration of F into dt over the time, depending on again whether the force is constant or variable. So like that, rotational or angular impulse that just becomes tau delta T or tau into T. Only thing is we don't use a separate symbol for it like we use a symbol J for linear impulse. Again, you can see conversion of pure rotation to pure translation happens this way. That the linear terms are replaced with angular terms. So force is replaced with torque, okay, for the sake of conversion of linear impulse concept to the concept of rotational impulse or angular impulse. Okay. So here tau is with respect to the fixed axis of rotation. So now the next thing, now since torque due to a force is equal to moment of the force, that is R cross F. That is torque tau due to a force F equals to moment of force R cross F, or the magnitude of torque is force into moment arm. So therefore, tau delta T becomes R cross F delta T. So we can say that angular impulse is equal to moment of linear impulse. So F delta T is now linear impulse due to the force. So we also have this relation that the angular impulse is related to the linear impulse by this relation, that angular impulse due to force F acting over time delta T equals to the moment of the linear impulse with respect to the axis of rotation. So moment of linear impulse is R cross F delta T. So whenever we take R cross something, it becomes the moment of that quantity. So this is the other important relation. Okay. So you can also say that magnitude of angular impulse will become magnitude of linear impulse multiplied by its moment arm. So again, this equation is analogous to this equation, that magnitude of torque is magnitude of force into moment arm. So like that, magnitude of angular impulse is equal to linear impulse multiplied by moment arm. So magnitude of angular impulse equals to linear impulse multiplied by the moment arm. So this is the concept of angular impulse. And once we are clear with this, we will see how this relates to the impulse momentum theorem for rotation. Just like we had impulse momentum theorem for translation, that the net impulse is equal to the change in momentum for a body. So there we were talking about linear momentum and linear impulse. Here we'll talk about angular momentum and angular impulse. So we'll see that when a rigid body is fixed about a certain axis, then the net angular impulse due to all the forces acting on it equals to the net change in its angular momentum. Okay. So just note this down systematically and try to understand the comparison drawn between the angular version and the translation version of these concepts of impulse. Impulse is force into time, or linear impulse is force into time. Similarly, angular impulse is torque into time. Now, torque is moment of force. So that's why angular impulse becomes moment of linear momentum or linear impulse. Concept of angular impulse is clear in this case, I hope.
Sir, 1 minute. Done, sir.
Okay, people done with this?
Sir, one doubt.
Yeah, tell me.
Sir, that how you multiply only delta t with f in that equation? Angular impulse equal to r into linear impulse.
Let us speak a little clearly. Slowly, I'm not able to understand what you're asking.
Sir, why you multiplied only at delta t with f?
To show that, see, this equation we have expanded now. That torque is basically what r cross f. So torque into delta t becomes r cross f into delta t. Now, while that force is acting, the point of application of the force is not changing. You understand me?
Yes.
The delta t multiply with what? The force when we take it inside that cross product. Okay. So when we multiply it with force, that becomes what? F into delta t becomes a linear impulse. Is it clear now?
Sir, and there is any symbol for angular impulse?
Which one? No, there is no specific symbol. So we just use tau delta t. Okay. So I'll explain this with an example. Okay, and this will become clear. So if you're talking about linear motion and how the concept of impulse works. So imagine you have a block on a surface, okay, And in this case, let's consider the surface to be smooth. But it's not necessary the surface should be smooth also. It can be a rough surface also. Now, if because of some collision or something coming and hitting this, a force F acts for a time delta t. So what happens? It gives the body a linear momentum. Okay. Now, like that, so this is the case of F into delta t is linear impulse. Okay, due to force F acting for time delta t. Okay, and the effect of linear impulse is linear momentum change. It transfers linear momentum. Okay. But now, like that, suppose this was instead something like a rod which is hinged over here. Okay. And now what is happening is that same force is acting over here for time delta t. So what is happening is that force is now creating a torque with respect to the hinge, because this is my moment arm for that torque. So that is going to now create angular momentum for it. So with respect to the hinge, okay, so let's say there is a hinge at O. So the angular impulse, okay, due to that force F acting for delta t amount of time, the angular impulse will be tau into delta t. So that will be equal to R cross F into delta t. So it will be basically R cross F delta t. So the angular impulse equals to moment of linear impulse. So this is the equation that is analogous to the equation of torque. That when we write torque is equal to R cross F, the torque due to a force equals to moment of force. So the magnitude of torque becomes force into momentum. Okay. So here also the magnitude of angular impulse will become the linear impulse multiplied by its momentum. And what effect this angular impulse has? The effect is to transfer angular momentum. It makes the body try and rotate. So it changes its angular momentum. Whereas the effect of linear impulse was to transfer what? Linear momentum to the body. Okay. So again, this makes it clear the relation between angular impulse and linear impulse. Okay. So translation. Okay, and in that the concept of linear impulse versus force, okay, and pure rotation, rotation about a fixed axis, and the concept of angular impulse versus torque. Okay. And finally, the relation between angular impulse and linear impulse. That angular impulse equals to moment of linear impulse, just as torque equals to moment of force. Okay, so hope this visual example also gives you better understanding of this. Next, we'll also see how to apply this in numerical situations, in solving situations where the net angular impulse results in a net change in angular momentum. So once we see those type of numerical problems, this will become even more clear to you. Okay.
Sir, 1 minute.
All right.
Done, sir.
Now the impulse momentum theorem. So again, you can see that when we explain this theorem for pure rotation, it is just like you have taken the theorem for pure translation and converted it to a rotational equation by changing the parameters to their rotational versions. Okay. So in pure rotation, it is that net angular impulse equals to the change in angular momentum, and both are with respect to the fixed axis of rotation. Okay. So basically, it is summation of tau delta t for all external torques, okay, is equal to change in angular momentum, or delta of I omega, or I into delta omega, because obviously I is remaining constant. Whereas if you were to compare this with the case of pure translation, the idea is that the net linear impulse that equals to the change in linear momentum. Okay. So summation of F delta T for all forces, all external forces, is equal to change in linear momentum, or change in MVCM, which is M into delta VCM, like this. So this equation is just the angular version of this equation. Okay, so note this down quickly, then we'll see application example of this. Okay, so now let's look at an example with a direct numerical application of this concept. So what we have is a thin uniform rod. Its mass is, let us say, 5 kilograms, and its length is 2 meters. It's suspended vertically from a free hinge about which it can rotate. So free hinge at the point O on top, like this, okay, about which it can rotate in that vertical plane. Of the diagram. So gravity is acting downwards like this. So the plane of the screen is a vertical plane. Now it is just about above the floor. It's kind of touching the floor without hitting it. So imagine that kind of situation here. So this is a frictionless surface. Now we have a sort of block, but the block size is negligible compared to the length of the rod. So the rod is initially at rest. Now a block of mass small m equal to 2 kg and negligible size compared to the length of the rod is sliding at a speed of, let us say, 2.5 centimeters per second on the smooth floor. Now after impact, the block stops and remains at rest. We want to calculate the linear impulse, okay, on the block due to collision with the rod. Then we want to calculate the angular impulse on the rod due to the collision. And then we want to calculate the angular speed, say omega naught, of the rod just after the impact. These quantities we want to calculate. Okay. So we will apply the above theorem, the impulse momentum theorem over here. So just take down the basic data of the question, then I'll explain this question how to work it out. Okay, so let's work out this question. So what we'll understand here is that,
Sir, can you take up, please?
yeah, sorry,
Sir, can you show that question? No.
see the question. Okay, just a minute. Yeah.
1 minute. Done, sir.
So now, as this block comes in contact with it, okay, so we will imagine the situation such that actually just try to think of the block as something of much smaller size, so that its own dimension will not matter compared to, so the block is more like this. Okay. So now as it comes in contact with the rod, what happens is that there is a impulse due to collision that acts between them, an action reaction pair that acts between them. So as the block will come in contact with the rod, they will apply equal and opposite collision impulse on each other, F delta. And of course, the block's weight is being supported by the ground below and all that. Okay. And immediately after the impact, therefore, what is happening is that the block would have come to rest. Whereas the rod has started rotating. So the rod has developed this angular velocity omega naught, okay, whereas the block has come to rest. Whereas if you also consider what was happening before the impact, just before the impact, so just before the impact, the block had a linear momentum. The rod was at rest. So during this time, you can see that if you take this as your positive x-axis, okay, for the block, this is equal to that net impulse equals to change in linear momentum. The impulse is acting in the negative x direction. The momentum is changing from mv naught in the positive direction to 0. Okay, so F delta t, the magnitude of the linear impulse acting on it, is mv naught. So that is according to whatever the values are. See about. Okay. So it was 2
Sir,
kg.
first one diagram is before at impact and after impact. No?
Sorry, what happened?
So that diagrams are of before, at, and after impact.
Not able to understand what you're saying. Speak a little louder.
Sir, that diagrams are of before, at, and after impact. No?
This is BR. This is before impact, just before. This is during impact. And this is just after impact. Got it now? Okay. So that is for the block what is happening. Whereas for the rod, what is happening? this linear impulse is acting through this point F delta t, whereas the rod is having a hinge over here. So it's having a moment arm of L. So it's creating an angular impulse. So that angular impulse is equal to linear impulse multiplied by the moment arm. That is a perpendicular distance of the line of action, which is L. So the angular impulse acting on the on the rod is becoming F delta t times the length of the rod. This is the angular impulse due to impact about the hinge. The hinge is at this point. Okay. So that is becoming equal to how much? From here you transfer the value of linear impulse. So it is mv0 into L. And as a result of that, the net angular impulse is equal to change in angular momentum. So in the initial picture, you can see the angular momentum of the rod was 0. In the final picture, the angular momentum of the rod is I omega, that is capital ML square by 3 omega naught in this sense. In the initial picture, you can see the linear momentum of the block was mv naught. In the final picture, you can see the final linear momentum of the block is 0. So for the block, the change in linear momentum is minus mv naught. For the rod, the change in angular momentum is plus I omega naught, but in the counterclockwise sense. Okay. So now this tau delta t should be equal to delta L. So small m v naught L is capital ML square by 3 omega naught. So the angular speed of the rod just after impact will become 3 times small m by capital M into v naught by L, and then we can just substitute the values. So this is the answer to the second part. The angular impulse due to the collision on the rod is this much, and as a result of the angular impulse, the angular velocity of the rod immediately after impact is becoming this much. Whereas the first part, the linear impulse on the block due to the collision is this much. So these are the 3 parts solved out. So I'll just minimize this a little. You can go through the whole thing from the beginning with the diagram. So this is a very basic kind of example to understand the concept of angular impulse. Okay, its relationship with linear impulse, and also the impulse momentum theorem in the case of pure rotation, that the net angular impulse is equal to the change in angular momentum. Okay, people. So hope this example is clear. This application example is clear to all of you. Okay. So in like
Sir.
yeah.
Sir, one doubt was there.
Yeah, tell.
Sir, how that negative sign came before f delta t? Linear impulse.
That is because now we have taken the positive x direction towards the right now. So on the block you can see now that the initial momentum was like this. So the initial momentum will write with sign convention as plus mv naught because we are taking this as our x-axis. Okay.
Yes.
Then the impulse that is acting is towards the left now.
Okay,
so
sir.
The impulse we should write as minus f delta t. Okay. And the final momentum was 0. So the change in momentum becoming minus mv naught now.
Yes, sir. Correct.
Okay, so just to generalize this concept now, so if we have any rigid body, okay, which is having a fixed axis over here, okay, and then a linear impulse acts like this, f delta t, whose line of action is like this. So the point of application of that force is this. Okay. So the torque because of that force is r cross f. Okay. So the angular impulse because of that force becomes r cross f delta. So in other words, if we drop this perpendicular here, this perpendicular distance only is our r sine theta, which is the moment arm. So the magnitude of angular impulse becomes the magnitude of linear impulse into r sine theta, which is the moment arm. And that's the concept, that angular impulse is equal to linear impulse multiplied by moment arm, or moment of linear impulse, and net angular impulse is equal to change in angular momentum. So the effect of this angular impulse is to give it an angular momentum in this sort of direction. So we will continue from this point in the next lecture. Okay, and
Sir, 1 minute.
yeah. In the meantime, please practice questions from H.C. Verma related to angular impulse and angular momentum. Okay, so there are questions up to question 34 in H.C. Verma. Sorry, not 34, 44. Rotational Mechanics chapter. We'll do these questions. Okay. Right, so that's it for today's session, people. Thanks for attending. Wish you all the best. Have a nice day.
Thank you, sir. Bye, sir.